So, welcome to chapter 3. These early sections of 3 will be a couple short videos because we just need the individual pieces before we put it all together. So, up until this point, we've practiced some algebra, we've practiced some derivatives, and now we're going to see why we care, assuming you do. So, what we do with derivatives often is tell where interesting things happen. So we can take our function and use that to tell if the function is increasing, decreasing, where we have local maximums and minimums. We have something called inflection points, which we'll get to. We can see kind of what our graph looks like, and seeing what our graph looks like tells us where things happen. So if we have a parabola, it's a cost equation, our cost goes up to here and then it goes down. We want to know what that point is to see how many things do we need to sell before we make money or before we stop losing money, as the case may be. So that's what these functions help us with. They do other things as well, but that's the first example I came to. So we have increasing and decreasing functions. If the function itself is increasing, that means its first derivative is always positive. For all x in the interval or on the graph. If it's decreasing, our derivative is always negative. And if you think of these two graphs, the first one is a positive, so we go up 2 over 1, up to, I need to move that, 2 over 1. So my first one here, which is very ugly, but that's okay. You could see the function is always increasing. For the other one, we go down 3 to the right 4. I did not think this function through before I drew it, before I chose it. This one, f of x equals negative 3/4 x, is always decreasing. Lines are the easiest thing that are always one or always the other. We'll have some other functions, specifically our logarithmic and exponentials, but that's, I think, next chapter. So we'll get there in a bit. Most of the time, though, our function isn't going to be all increasing or all decreasing because those aren't interesting. So we'll have increasing or decreasing intervals. We'll get to critical values in a sec. So let's have a very nice little parabola. Okay, a very ugly parabola, but that's all right. Sorry, trying to draw it. Yep, okay, that is a very ugly parabola. So this parabola, we can see our slope will be positive until we get to this point here. And then we take a turn and it's always going to be negative. So we can say we're increasing from negative infinity. So we read from left to right until my x value is at 3. And we always put the open brackets or regular parentheses for here because it keeps increasing to 3 and then 3 something else happens. And then we're decreasing from 3 to infinity. So we look at the domain or our x value. So we tell it where it's increasing, decreasing. So up until this point, if you wanted to figure out where your parabola was increasing or decreasing, you had to use an equation that'll give you the vertex. And honestly, sometimes those can be really nasty. They're hard to solve for. They get very messy very quickly. So there is an easier way. I always feel bad when I teach college algebra and pre-calc because I have to show them how to do it the hard way when I know there's an easier way out there. All right, let's see if I have this popped open. I do. This is the function we're looking at, this guy here. So when I have written there, a much better drawing than I could ever do. We have, can I zoom in a little bit? Yeah, there we go. So here's our parabola. We're very clearly decreasing until we get to x equals 2. And then we increase after that. So let's look at that with a derivative. Go this way. Our critical values are where something interesting happens. And that happens at where the first derivative equals 0. So let's find the critical values for this function. And you could have 0, 1, infinite number of critical values. It just depends on what you're looking at, what your function is. This one's only going to have the 1. All right, so I take my derivative. Hopefully we're pretty good at those by now. All right, so derivative, the first thing gives me 6x minus 12, and the 14 is a constant, so it goes away. And we want to set this equal to 0. So we say 6x minus 12 equals 0, and solve this whatever way. Easiest way is just to say 6x equals 12, x equals 2. Hey, that matches the thing we said. So we said the critical value happens at x equals 2, and it did. Okay. If I want to figure out where that point is, so we want the y value, you just plug it in. Oh, I didn't solve this beforehand. And I don't know where my calculator is. Okay. 2 squared is 4. 4 times 3 is 12 minus 24 minus 14 plus 14, which gives me 12 minus 10, which is 2. I really hope it's 2. Yeah, okay. I could have looked, I suppose. So we have a crit at 2, 2. That's where our critical value happens. So most of the time when we analyze our functions, we're going to find our critical values first, and then we deal with the rest of it. So we'll eventually use the second derivative, but that's a couple sections from now. Whoops. If I want to see where this is useful, I'm going to make a little number line and plug in 2. And so I know I have a critical value here. And then I'm going to choose something to the left of 2. If I can choose 0, I always choose that. And something to the right of 2, so something bigger. Let's choose 3. Now, we're going to tell where our function is increasing or decreasing based on our test values. We come back to the function, we know it's going to be decreasing until 2, and then it increases. But let's see what that happens with the first derivative. I think I'm getting into the next section stuff, but it's okay. All right, so if I take 0, plug it into my first derivative, I get f prime of 0, come on, pen, equals 6 times 0 minus 12. And we really only care if this is positive or negative. So a lot of times you don't even have to do all of the calculation. You can just look at that and say, oh, that is clearly going to be negative. If I wanted to solve it out, I get negative 12. So we care about the sign more than the value. So over here, we're negative. If I plug in 3, come on, pen. Six times 3 minus 12. 18 minus 12 is 6. And again, I care about the sign. So this is positive. So I like to see what that means graphically. So my slope is negative, so it's decreasing until I get here. And then it's positive, it's increasing after that. And if you draw it like that, it kind of looks like a parabola. It's not exact, of course, but it gives you an idea of what your graph shape should look like. And if we flip back to this screen, whoops, here we go. That is exactly what our graph shape looks like. It doesn't give us the y value here, but we don't really care. We're just getting an idea of what our graph is doing. So that's this function. Let's look at the critical values of the next one. And we'll come back to these in a second, or in the other videos as well. Oof, okay. So we can see our x cubed function here has two critical values. So it's 2x cubed minus 9x squared. So first derivative. Dot, 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 6x squared minus 18x. So we have a square, we know we're going to have two critical values, or up to two critical values. So set that equal to 0, 6x squared minus 18x equals 0. Factor 6x times x minus 3 equals 0. And now we say, okay, set both of these equal to 0. I get 6x equals 0, or just plain, come on, x equals 0, x equals 3. So we should have critical values at 0 and 3. You know, I think I'm really doing all of 3, 2 on accident, but that's okay. If we have two critical values, now we need more test points. You always want to find them in between. We can't use 0 because 0 is one of our critical values. So I'm going to choose -1, +1, and 4. Maybe. Come on. Okay. Plug these into the first derivative. So if I have f prime of -1, again, I only care about the sign. The first thing will always be positive, no matter what I toss in there. Second thing is also positive, so that is going to be a positive value here. So we're increasing. If I plug in +1, okay, a positive and a negative. In this case, I do have to calculate a little bit. 6 minus 18 is definitely a negative. We already know what this is going to be, but let's play it out. 4. All right, 6 times 16. Let me find my calculator. I'm not doing that in my head. Gives me 96 minus 18 times 4, 72, which is very clearly positive. So this tells me I am increasing, decreasing, increasing. So our function should look something like that. So if we want to report where we're increasing, the places where we have the positive. So from -infinity to 0, and I'd never leave myself enough space. And from 3 to infinity. No, hang on. So we have a union symbol. Maybe. Come on, pen. You should have union 4 to infinity. The pen doesn't want to agree with me today. Okay. We're decreasing from 0 to 3. There we go. I really need to get some new tools, but they're expensive. And they are not fun to buy. So we're only decreasing in one interval, so that only gets the one interval. And I think I've mentioned before, but this is a union. It means and. So it's increasing in this interval and it's increasing in that interval. And if we look at our graph, where did you go, graph? There we go. Desmos is great for looking at these. I don't have to draw them anymore. We can see, yeah, we're increasing until we get to 0. Oh, okay, I can't point at it with my pen, sorry. We're increasing till we get to 0. From 0 to 3, we decrease, and 3 on, we increase again. So I really did 3.2 here, so I'm going to label this as 3.1, 3.2. I didn't even think about it. These two things go together so well. It just kind of happened. So I'll do 3.3 next.